Okay, let's make it a little bit tougher here. I got a couple of fractions. Of course, you look at this, and I want to start with the complicated side, and I see the left side, right? Got fractions involved. So I'm going to try to combine those, and it looks like I need to combine those and get rid of the fraction. So anytime you have multiple fractions added together, my suggestion to you would be to find a common denominator, combine them into one fraction first. So if I have a common denominator, I would say that it would be 1 plus sine A, 1 minus, it's alpha. 1 plus the sine of alpha, 1 minus the sine of alpha. So that's what I'm going to start with on the left-hand side. Common denominator is this. 1 plus the sine of alpha. See a difference of squares there? That's probably going to go away, isn't it? Alright, so with that in mind, then now I need to change my numerators. And it looks like in order to get up, I have two terms in the top. In order to get up to the common denominator on the left side, I have the 1 minus sine alpha, I need the 1 plus sine alpha, right? So I'm going to take 1 times 1 plus the sine of alpha. The second term is going to be plus 1. And it looks like in order to get up to the common denominator, I have the 1 plus sine alpha already. I need the 1 minus sine alpha now. So there's the left side combined into one fraction. That needs to be shown that it's equal to 2 secant squared of alpha. Alright, now let's do a little distributive property on the top. Let's go ahead and square out the bottom. I'm going to do both of those in one step here. So I really have 1 plus the sine of alpha plus 1 minus the sine of alpha on top. On the bottom I have 1 minus sine squared of alpha. And I need to show that that's equal to 2 secant squared of alpha. Get a little closer. Alright, combining like terms on the top. I have sine alpha and a negative sine alpha, so those go away. That means I'm left with 1 plus 1. There's a 2. Convenient, right? Because I end up with the 2 on the right side. That's probably where that 2 came from. That's over 1 minus sine squared of alpha. I need to show that that's equal to 2 secant squared of alpha. So it looks like maybe I have the 2 taken care of. It looks like I need to show that this stuff somehow is equal to secant squared. Alright, I got 1 minus sine squared, so I'm going to pull back on a little side knowledge here. I know that sine squared alpha plus cosine squared of alpha is equal to 1. So if I subtract sine squared from both sides, I have cosine squared of alpha now on the left. So those go away. And that is the same thing as 1 minus sine squared of alpha. And I want to do that anytime really that I see squares show up. I'm probably going to use Pythagorean identities. So now that means that instead of writing this as 2 over 1 minus sine squared, I can write it as 2 over cosine squared of alpha. And that's convenient because I know that 1 over the cosine is the same thing as secant. So I can really say here that 2 secant squared of alpha is equal to 2 secant squared of alpha. Put a little check mark next to it, you're done. Well done. So all the work here is what we're looking for. When I'm looking through this stuff, I want to see all of this manipulation here. I want to know how you got. There should be no guesswork by me as to how you got from one step to the next. If there's any fogginess in my mind, if there is any doubt in my mind of how you got from one step to the next, it's probably not a good proof. So the idea is always show more work than you need to whenever you're doing these proofs. Let's do this problem here. Same idea. Looks like a fraction on the left. That definitely looks terrible compared to the right side. So let's go ahead and let's combine them. Common denominator is going to be 1 minus the cosine of beta. 1 plus the cosine of beta. Looks like the first term I'm going to have 1. And I've got the 1 minus cosine on the bottom, so I need the 1 plus the cosine. Second term, I'm going to add 1 times. And it looks like I already have the 1 plus cosine beta, so I need to multiply by the 1 minus cosine beta to get it up to the common denominator. So there's the left side combined into one fraction. I need to show that that's equal to 2 cosecant squared of beta. Alright. Top, I'm going to go ahead and distribute out the 1s. I really need to do that. there's the top distributed out. The bottom is a difference of squares again. That's 1 minus the cosine squared of beta. I need to show that that is equal to 2 cosecant squared of beta. Alright, let's combine some like terms here. I see that I have a cosine b and a minus cosine b. Those go away, and once again I'm left with a 2 on the top. I'm left with 1 minus cosine squared of beta on the bottom. I need to show that that's equal to 2 cosecant squared of beta. Alright, now I got 1 minus cosine squared, so off to the side I'm going to say, well, I know that sine squared beta plus cosine squared beta is equal to 1. So that means if I subtract cosine squared of beta from both sides, I'm going to be left with sine squared beta on the left, and that's the same thing as 1 minus the cosine squared of beta on the right. So now I can go through and I can replace. I can say, alright, back to work. Instead of 2 over 1 minus cosine squared, I'm going to call that 2 over sine squared of beta. Now, the last thing that I know is that cosecant is the same thing as 1 over the sine. So I can rewrite this as, instead of 2 over the sine squared, I can write it as 2 cosecant squared of beta, and that's equal to 2 cosecant squared of beta. It all checks out. There's my proof. So that's how to do a couple of problems that involve fractions and how to combine fractions with a common denominator in order to prove or verify these identities.